Hello, good morning. Here we are yet again for another lovely session of CENG 4412 Steel and Concrete Design. So today we're going to actually tackle block shear rupture. We've mentioned it before, and in previous lectures we've described what it is, but we haven't actually looked in detail about the theory or the calculations, elements in the code dealing with what block shear rupture is. So in this part of the lecture, so I'm going to have a part 1 and part 2 of this lecture. This is going to be the 5th lecture or 5th lesson in the series, and this is going to, so part 1 is of the 5th portion is going to focus on block shear rupture. Then later today I'll record a part 2, and that will cover some notes on staggered bolts and how to handle connections with staggered bolts. So for this video here, though, I want to discuss the rationale behind the block shear limit state and learn how to calculate the capacity of a connection in block shear, and then discuss the rationale behind the UBS factor. BS standing for block shear. So let's first do a review of what block shear is and look at the failure mechanisms therein. So block shear. Now, as we previously discussed, we have the fracture limit state. Well, we have the yield limit state, the fracture limit state, and the block shear limit state. The yield limit state is where you are stretching something and causing excessive deformation. The fracture limit state is when you are cleaving across the entire cross section. The block shear limit state is where you are tearing a chunk out of a section. So let me draw out what something would look like if it's failing in a block shear. So if you have something failing in block shear, imagine I have a plate and I'm going to pull on it and it's going to fail in block shear. Imagine you have something like this. So you might have something kind of like this, where it's tearing out along bolt holes, kind of like this. Imagine tearing a chunk out of a plate and it leaves a piece like this, something like this behind. Now, of course, in the real world, it wouldn't be so clean and neat, but for the purposes of our discussion here, we can look at sort of an idealized behavior. Here. So imagine I have, and both of these pieces would continue on in different directions. This would most likely be a member that goes on much further, like this. And then I have the piece that I'm tearing out. That would be, maybe this would be something that would be bolted to another member, etc. But anyway, I'm tearing out one chunk of plate and just tearing it out, and we'll look at the failure modes present here. So something like this, and something like this. So I'm going to, if I want to tear this piece, this chunk of this plate out of this plate, and it could be a plate or it could be a web or a flanger, anything connected in tension, let's look at the forces. Let's sort of do a rough free body diagram. Well, I have my actual P force that is pulling this thing apart, P and P. But what's actually pulling this thing apart? Well, what forces are present here? Well, if this thing is going to fail, if I'm going to tear this chunk away from this chunk, on this plane, I'm going to have tension. On this plane, I'm going to have tension, so I have a lot of little force arrows here, tensile force arrows. And if I can manage to write arrows properly or draw arrows properly, lots of little tension arrows. And then on this plane here and this plane here, I have shear. So I have a shear plane here, and this plane here. I have shear on this plane here and this plane here. Okay, so again, I have a combination of shearing and tension. So if we are calculating our capacity in block shear, we're going to have to consider both the force required to shear this plane, the force required to shear this plane, and the force required to make this plane fail in tension. Okay, so let's look at some notes on this. Well, is this going to be a yielding or a fracture phenomenon? What do you think? Yielding or fracture? Again, yielding is where you're stretching something to. It's fracture. Yes, this is a fracture phenomenon. So, again, fracture is much more critical than yielding. Yielding, you're only you're basically causing excessive deformation. That can be detrimental, especially if it's going to cause bricks to crack or drywall to crack or window frames to buckle or something. That's not a good thing, but it's not catastrophic. Fracture is catastrophic, so we use a lower resistance factor here. So this is going to be a fracture phenomenon. Oops, I erased part of my plate there. This is a fracture phenomenon. So therefore, our phi factor is going to be equal to 0.75. For this, we're going to use a more conservative resistance factor because this is kind of critical. Because it's a fracture phenomenon, it's a very bad thing if this does fail, because it's going to fail completely and dramatically. It's actually going to tear into two pieces. Again, this is going to be a tearing limit state in the connection region. Limit state in connecting region. In connection region. And let's see what are some other things. It's most common in connecting elements. Oh, okay. Again, tearing limit state in the connection region. Okay, it's a tearing limit state in the connection region. And we do have some other things we'll discuss as well. Okay. So it is so we've seen what kind of failure it is, but where does it occur? Well, it's most common in connecting elements, in tension, and thin web connections and W shapes. And W shapes. And thin web connections and W shapes. And so one side is going to rupture while the other yields. One side ruptures while the other yields. And we'll explore this. Okay. So here, let us look at the overall approach here, our block shear rupture approach. Block shear approach. Well, again, we have different, the thing about this is that we have different failure modes for different surfaces. So the way we approach this is to sum up the strengths of each individual plane. So the approach basically, again, is to sum up the strength of each individual plane. So again, if we look here, we have a plane in shear, a plane in shear, and a plane in tension. So that's what I mean. So we're going to calculate the capacity of the plane that's in shear, or the planes that are in shear, and we're going to calculate the capacity of the plane that is in tension. And we are going to say that if in order for this, the only way this thing is going to tear out is if we apply enough force to break both of those. So both of those are going to contribute to our supply of available load. And so that's how we're going to calculate the capacity of these connections in block shear rupture. Okay, so let's see here. And first, we're going to look at shear. We're going to calculate the capacity of each of the planes, and the shearing planes will be the first one. We'll have shear, and here. Let's consider this. Shear. We have this, we're going to look at this both in terms, we're going to calculate both in terms of shear, fracture and yielding in shear. So we're going to have 0.6 FU, 0.6 FU A and V. And let's look at this. Let me annotate this, or let me not cover that up while I annotate it. And here, first let me label this as shear fracture. So this is shear fracture. So we're going to be calculating both shear fracture and shear yield. Shear fracture, and what are these things? Well, this here, this 0.6 FU, F sub U. Again, your yield stresses, these are stresses in tension. And as we'll see later, the capacity of materials in shear can usually be considered as 60% of their capacity in tension. So to calculate the shear capacity, the shear yield or shear ultimate stress, we simply multiply the tensile stress, the tensile capacity, by 0.6. So this is going to be the ultimate stress in shear. And this A and V here, this is our shear area. The area of the net shear area, let me say net shear area. Net shear area. And so this is the net area that's going to be in shear. Okay? Next, and then we'll also have to look at this in terms of yielding, because we can have both a shear yielding or a shear in fracture. So in the tension plane is essentially always going to be in fracture, but the shear plane can be in either fracture or yielding. So again, we can have what we discussed previously, and I'm just going to go over the basics first, and then we'll look at how this is actually implemented in the code. So we can have the shear. We can have shear failure, or have shear capacity that can either be yielding or in fracture, So again, we're still looking at the shear, but we can have shear fracture or shear yielding, or 0.6 Fy. This is going to be a yield stress, AGV, a gross area. This is going to be our shear yielding. Shear yielding, where this here again is going to be, if we take the yield stress and multiply the yield tensile stress and multiply by 0.6, we get the yield shear stress, or the shear yield stress. And then this is the gross shear area. So for yielding, we're going to use gross area, and for fracture, we're going to use net area, just like we did previously when looking at fracture and yielding. This is the gross shear area. This is the gross shear area. And then we've looked at in shear, we have to consider both the fracture and the yield. However, for tension, we don't need to consider we won't be considering simply a yielding. We're going to only be looking at a fracture case, because on the shear plane you can get either fracture or yielding, but on the tension plane it has to be again, because if we look at this plane here, this can stretch a lot on this plane. We can get stretching of this member here in shear, but this member, on the tension, the only way this is going to fail is in fracture. But the second way, but we'll also be considering the capacity in tension. And I know this is a bit confusing, but I think it'll make more sense when I actually look at the equations inherent in the code, or present in the code. And the tension capacity is going to be this factor, or is going to be something called UBS, FU, ANT. So what are these? Let's annotate this. UBS. This is a factor or a coefficient This gives a uniformity of, it's basically a uniformity of stress factor. Uniformity of stress factor. And we'll discuss this briefly. We'll discuss this later, I suppose. If uniform tension stress, if you have uniform tension stress, then UBS is equal to 1.0. And this, for a detailed discussion on this, please see the commentary. And then, however, if it's non-uniform, we will use 0.5. UBS is 0.5. And then this is the FU. FW is the ultimate strength in tension. The ultimate strength in tension. And ANT is the net tension area. The net tension area. So what I have laid out in this slide and the previous one are the various ways that we get capacity in block shear. So in block shear rupture, the tension plane is only going to be, we only consider it for fracture, but the shear planes, we'll calculate their capacity for both fracture and yielding, and basically go with the smaller one effectively. But so these are the different pieces of the overall arching equation that we find in Chapter 4 of the AISC Steel Manual. And so let me next go let me then next go to how all of these fit together in the actual code. So let's look at how these are all working together, how all these moving pieces come together in the AISC code. So combining together in the code, combining them in the code. Or if we combine them, we get the AISC code, or what's in the AISC code, approach. And there is now, we're going to put all these together into one big scary equation. Well, not big and scary, at least compared to some of the things we see later. Wait till we get to wait till we get to beam design. You don't. I just heard. I don't want to know. We will in time. It's not that bad, depending. These are all combined together in equation J4-5. J4-5. And this is found on page 16.1-138 of the 15th edition. Of the 15th edition of the AISC Steel Manual. Now, let's look at the, let me write the full thing out. Now, the nominal resistance, R sub n. So this is a bit long. It is. It's essentially an inequality in the sense that the way these inequalities work in the code is that you calculate both sides of them and go with the smaller one for your capacity. This inequality is not saying your load is less than demand or your capacity is less than demand. It is saying that you have two different possible failure modes, and you calculate your capacity according to each side of the inequality, and your capacity is going to be the lesser of these two. So Rn is basically let's see, maybe I can write this as, I'll write this as a words first. This equation is basically constructed as to say a shear fracture mode, shear fracture capacity is less than or equal to shear yield capacity, or shear fracture failure mode is less than or equal to shear yield failure mode. And so you calculate both sides of the equation you calculate both sides, and your connection or your element will only be able to stand the lesser. Your element can only take the lesser of these two.
So why is it an inequality then?
Yeah, I know the inequality is not perfect here. The question was, why did we use the inequality? We essentially just, the code does that. I know it's not necessarily perfectly mathematically accurate. One quantity isn't always less than the other. We basically go with the way this works is this one will most of the time control, but this is sort of an upper value. Most of the time, this is the one that's going to control, but we have an upper value that says, okay, so essentially we'll say your capacity is this failure mode, but you're not allowed to go over this failure mode. That's why we're using the inequality. But the actual equation here is Rn is equal to 0.6. This is kind of long, so I'm going to write it a bit small. Rn, the nominal resistance, is equal to 0.6 FU A and V, FU A and V, plus UBS times A and T, times FU A and T, and then this must be less than or equal to 0.6 FY AGV, plus UBS times FU ANT. Okay, so let me again annotate this so we know what all these things are. And I've already discussed these, but just to make things really clear, or hopefully it may be clear as mud, we'll see. This will be our shear fracture, the fracture capacity on your shear plane. This would be the shear yielding case. Shear yielding. But then in both cases, we consider tension fracture. This is tension fracture and tension fracture. Tension fracture and tension fracture. Okay.
So they don't have
The fee, we already discussed that previously. You do have to add a fee to this. This is just the equation for the nominal capacity. To actually get your factored capacity, you take this and multiply by 0.75. So yes, the actual allowable load, the actual allowable factored load is going to be equal to or no greater than your fee times this, and your fee is going to be 0.75. And that is also listed in below this equation. You can see that on page 16.1-138, we do multiply this by 0.75. And if we get to the example problem that I have, we'll be using that. Okay. So next, I would like to discuss. I'd like to discuss a bit what this UBS thing is. So all this stuff here, net shear area, that's not too difficult. Net tension area, gross area, that's all fairly straightforward. But UBS does need some discussion, and the commentary does go into this in great depth. But and it goes into it in greater depth than we'll have time here in class. But I do want to discuss what this UBS thing is. What this factor really means. So here, UBS. This UBS factor. Now, notice this is something that we're going to be multiplying by our tensile capacities. So it has something to do with tension fracture capacity, and the smaller this number is, the smaller the UBS is, the more conservative. If UBS is 0, we would actually be assuming that tension plane would be carrying no load. So the smaller the UBS is, the more conservative this is. So again, the UBS is a factor to take into account, non-uniform tension stress. And so what does that mean? If tensile stresses are uniform, in an ideal case, then UBS is equal to 1.0. UBS would be equal to 1.0. But what if they're not equal? And why can they not be equal? Or in what cases would they not be equal? Well, this is where, again, similar to some things we've seen previously, where we discussed the shear lag factor, you get non-uniform stresses when you have localized concentrations of stresses. So imagine you have, say, an angle. Imagine I have an angle iron. Here's the flange, and here is the web. And I'm going to apply some there's some tensile stress here, and imagine it's connected with a couple bolts here to some other piece. Well, way far from our connection point, my stresses are uniform. I have a uniform stress like this. I have some sort of uniform stress like this. So no problem. However, if this thing is going to fail in block shear rupture, though, what is that element going to look like? Well, the actual failure plane, if it's failing in block shear rupture, is not going to be the entire section. It's going to be just this rectangle here that's going to try to pull out. And if it's going to fail, this plane here will be in shear, and this plane here will be in tension. So this element is being torn out. We would have, again, we would have shear here, and we would have tension here. Now, the shear has its own capacity, but in terms of tension, all of this stress here has to somehow flow there. So effectively, you're going to get a great deal of stress concentration. All this tensile load has to end up concentrated down here. We get stress concentrations. So, in other words, on this tensile plane, if we look at just the tensile plane of the shear block, if we look at the tension, so if we zoom in on this thing here, stresses on tensile plane of our shear rupture block, stresses on shear plane of rupture block. What does that look like? Well, I would have something like this. If I were to plot the stresses out, right from the left side of the rupture block, I would end up with something like this. The stresses would be more concentrated right toward the left end of the rupture block, and less concentrated toward the right end, because you have a stress sort of bunching up. You have a great deal of localized stress right here. So this is kind of, the UBS is kind of a fudge factor. Like, to actually calculate that is really difficult. If you really wanted to directly calculate that, you'd have to use some sort of either experimental model where you just you broke a bunch of the type of connection that you wanted to analyze, or more properly or more commonly, you would be using some sort of finite element model. But instead, what we use is we just sort of use a fudge factor to say if there is any kind of stress concentration, we use a UBS equal to 0.5. So if you have a bolted connection that is constructed in such a way that the entire section will have to fail in order to get this kind of, or it would have to fail uniformly. Say, for example, you had a plate and you were tearing out just the middle and there wasn't going to be much stress concentration possible, you could use a UBS of 0.5. But if we have any kind of stress concentration possible, or if we have a uniform stress, we'll use a UBS of 1.0. But in most cases, you will have some sort of UBS possible, or some sort of stress concentration possible. So you would be more conservative to use a UBS of 0.5. So again, this is actually kind of a fudge factor. We just basically say if at any time could have stress concentration, UBS will be conservatively considered to be 0.5. Now, in terms of where you actually, let me write this first, conservatively taken as 0.5.
Wouldn't every bolted connection have a stress concentration?
Effectively, yes. That's what I was gonna get at. Effectively, almost every bolted connection is going to have some form of stress concentration. In fact, pretty much the only way that I can think of that you wouldn't have some sort of stress concentration would be if you have a welded connection, and say, for example, if you had imagine you had a plate and you had a welded plate connected to something else, and you had a weld all the way completely along the edge of the member, completely along the edge of the plate. And in that case, you couldn't have any stress concentration in that member there because the connection takes up the entire length of the member. But in almost any kind of almost any kind of bolted connection, you are going to have some degree of stress concentration. And the actual UBS, now if you had something that was like, imagine you had imagine this was a plate instead, and you had just a whole bunch of bolts that stretched across most of the plate, UBS would probably be 0.5, or UBS would probably be over conservative for that, but it's difficult to predict the actual value. So we tend to just use a 0.5 as a conservative value. Yes, questions?
I'm just confused because Segui has an example with an angle, and they say with an angle you can say it's 1.
In certain cases, we can go into that in more detail, and certain textbooks, Segui, we reference sometimes, does say that you can use 1.0 for that particular example. I would have to take a look at why that is, okay? But again, there are certain cases you can use 1.0, and certain cases you can't use 1.0. Certain cases you have to use 0.5. This is actually an area where there is quite a bit of contention, even in the design of the code itself. If you read in the commentary, you'll see that this is something that engineers and engineering professionals actually disagree on. This is actually a rather contentious issue in the code. And different editions of the code have gone back and forth. Some editions saying you have to use 0.5, some editions saying you can use 1.0, and some providing other values. It's something like codes, again, are these are things created by human beings, and human beings can actually disagree. Even very skilled and educated human beings can have strong and educated opinions on what the proper value is. So as far as which is the appropriate to use, if you clearly have a uniform stress, use 1.0. If you clearly have a non-uniform stress, use 0.5. Everything in between, it depends. You may be able to conservatively use, you can always use 0.5 as a conservative value, but in terms of when to use each, read the commentary, use some engineering judgment, and you can read on more studies therein, and we can provide further data and examples. Okay.
Now, to what you mentioned, wouldn't that be because of the distribution of the connection of the bolts in an angle? For instance, you have in one plane you have the 2 bolt connection, and the other plane you have the other 2 bolt connection.
If you can, yes, if you connect both planes of an angle up, but it's rare that you're going to connect both halves of an angle up. But
The example is just one plane.
the example is just one plane, yeah. So that's a little trickier. I'd have to take a look at that example.
One more question.
Yes.
Earlier you mentioned that the smaller the UBS, the more conservative it is.
Yes.
Did you say that means that the less tension it can handle?
Yes. The question is, does that mean if the smaller the UBS, the less tension it can handle? Yes, exactly. So you're basically, the smaller you make UBS, if you use a UBS of 1.0, you're saying this connection or this element can handle this much load in tension fracture. If you use a UBS of 0.5, you're effectively saying this element can withstand only half of my previous value. Okay? Yep, you're welcome. Okay, so I do have an example I think we have time to work through. Now, here, so I'm going to use this particular example that we looked at in the previous lecture, part 3 of the previous lecture, which was recorded last night. So not ideal, but anyway, as part of this, and please see the previous lecture for this, we did calculate. We looked at in the previous part, we've already proved this, that it's good for, that the connecting element and the tension member are good for fracture and yielding. We proved that. So please see the previous lecture for where we go over that. And we also calculated the ultimate load, the ultimate factored load, the R ultimate, or the P ultimate. P ultimate here is going to be what? Let's see, where was that? The P ultimate, let's see, I'm trying to remember where that was. Yeah, let's see, the 200, yes, the ultimate load was 212.2 kips. So the P ultimate, not P nominal, P ultimate, the ultimate factored load. In the example problem, I gave us some dead load and live load, and we calculated that. The ultimate factored load is 212.2 kips in tension. So we have to prove essentially that our capacity is our capacity in block shear is equal to or greater than 212.2 kips. Okay, so let's work through this. First, I need to draw out the element that I'm going to assume will fail. And the failure plane that I'm going to assume is going to be this here. The failure plane, I don't want to put the failure plane here. I'm just going to check the angle here. In this particular one, it's probably it's going to be safe to say that I don't actually need to check this particular plate for. I don't need to check the plate for block shear, and the reason for that is that this is made of a stronger material of this, and this has much greater geometry, much greater cross-sectional area than this one. So there is no way that this one is going to fail in block shear before this one. And there is a certain amount of judgment that comes with this. Often you do have to pick some sort of failure plane or some sort of failure mode when designing or when checking block shear. And how I'm going to check this one is I'm going to assume that this chunk right here is going to tear out. I'm going to assume that everything here is going to be pulled away, and this section here is going to remain behind. And you have to think about this geometrically, you have to think about this physically. And I'm going to have to assume here that this chunk comes out, and the reason for that is I have to make sure that each bolt is being left behind. So I couldn't physically tear away just this piece because that would leave these bolts still holding onto this thing. I have to tear out every single bolt. And I also don't want to tear out. You might try to say, okay, what if I tear this way? But the problem with that is then I would have to be tearing out through the two flanges of our angles here. That would mean a much greater cross-sectional area would be failing, so that's probably not going to be critical. Anyway, there is that. Okay, so here, and let's see. So that's what we're going to be looking at. That would be the numerical example that we'll work with. And I think I might just describe that and then continue on in a second portion to describe this later.